This video will discuss several of the key properties of trig functions, taking a unit circle approach to do so. The first thing we're going to start with is looking at domain and range. Then we'll look at something called the period of a trigonometric function. We'll look at determining the signs in different quadrants. And then we'll develop what are called some fundamental identities, the reciprocal identities, quotient identities, and Pythagorean identities. And then we'll look at using these properties to evaluate trig functions at different angles. Before we determine the domains and ranges for our trigonometric functions, it helps to recall how these functions are defined. So remember from previous videos that the way we define the trig functions for an angle theta are to determine the point on the unit circle on the terminal side of this angle theta, and we say that the sine of theta is the y value of that terminal point on the terminal side. The cosine of theta is the x value. The tangent of theta is y divided by x, and then because of that we don't want x to be 0. The cosecant of theta is the reciprocal of the y, so we don't want y to be 0. The secant of theta is the reciprocal of x, so we don't want x to be 0. And then finally the cotangent of theta is x divided by y, so we don't want y to be 0. So for sine and cosine, we can see that there's no restriction on theta. We can choose any angle, and the y-coordinate is defined of this point, and the x-coordinate is defined. So sine and cosine, there's no restriction for the domain. So no restriction on theta for sine and cosine. And what that means then is the domain for those two is all real numbers, because we're thinking about the input values, and the input, which is theta, can be anything. So let's go down to the next page here and write the domain of this function. The sine function is all real numbers, and the domain for the cosine function is also all real numbers. Let's think about the domains for the others, which are slightly more complicated. Notice for tangent and secant, we don't want x to be 0. So whenever we have this restriction that x isn't 0, we want to know, well, what does that mean about theta? So think about x equals 0 up here and down here, right? So this upper angle is, one of the names for that angle is pi over 2, and the lower one is 3 pi over 2. So we could say pi over 2 plus any multiple of pi, right? 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2. And the negatives, negative pi over 2, negative 3 pi over 2, and so on. So I'm going to write this as pi over 2 plus any multiple of pi, where k is an integer. That's the same as saying odd multiples of pi over 2. And I should say theta is not those. So if x isn't 0, then theta isn't any odd multiple of pi over 2. So the domain for, let's see, tangent and secant is everything except odd multiples of pi over 2. but anything else is fine. So we can write it either of these ways. Then the others we want to think about are cosecant and cotangent, where y isn't 0. Here are the places where y is 0 on the x-axis, right? So if y isn't 0, then we want to know what's going on with theta. Theta should not be 0 or pi or 2 pi or 3 pi or any multiple of pi, any integer multiple of pi. Right. So let's write those down. So cotangent and cosecant, where we want to make sure that y isn't 0. That means theta cannot be an integer multiple of pi. You don't need to write these both ways, but I am, just so that you can see that either one is fine. Okay, then let's think about the range for each of these things. If we're thinking about the range for sine of theta, we're thinking of the values that y could have on the unit circle. Because the outputs for that function are exactly the y values on the unit circle, which would mean that y has to be between -1 and 1, but it could be either of those values. And another way to write that is that the absolute value of y would be less than or equal to 1. It's the same thing. And similarly, the range for cosine of theta would be the values of x on the unit circle. And the values of x on the unit circle, we would have x is between -1 and 1, which means the absolute value of x is less than or equal to 1. So the range for sine is everything between -1 and 1, and the range for cosine is also everything between -1 and 1. It may seem awkward to be talking about the x values as the range, but think about the range as being the outputs. And the outputs for the cosine function are the x coordinates on that unit circle. So usually we think about y values as the range, but really what you want to think of is more generally the range is the set of outputs. So the range for these first two is from -1 to 1. And then let's think about secant and cosecant. If we know that sine of theta is between -1 and 1, that means the reciprocal of that, let's write it this way, the absolute value of sine is less than or equal to 1. So the reciprocal, which is the same as cosecant, should be greater than or equal to 1. Right? If a value is less than 1, then its reciprocal would be greater than 1. So that means that cosecant could actually be greater than 1, or cosecant could be less than or equal to -1. So we get all of the values that are outside of the interval from -1 to 1. So let's write it this way, -infinity to -1 union 1 to infinity. Similarly, secant would have the same range because we would be doing the reciprocal of the cosine function. And the cosine function itself was between -1 and 1, so the reciprocal would end up between negative infinity and -1 and 1 to infinity. All right. So then we've got the tangent and cotangent functions, which are slightly more complicated. Let's think about this. If theta is in quadrant 1, for example, if theta is close to 0, then x is close to 1 and y is small and positive. So if we look at y divided by x, that's going to be closer and closer to 0. So as theta gets closer and closer to 0, y divided by x is going to get closer and closer to 0. And when theta equals 0, we will have exactly 0. But as theta gets closer to pi over 2, then we have y is close to 1, but x is small positive. So if y is close to 1 and x is small and positive, what we're going to get is that ratio will get larger and larger. But positive. Right? Because a fraction with a really small denominator is going to be actually a large value. Similarly, in quadrant 2, for example, the ratios are going to be negative, but we're going to have some ratios that are close to 0 and some that are large, large, large negative. So what we've argued is that the range for the tangent function is negative infinity to infinity, and the argument about the cotangent function would be similar. So those two actually take on all the values. We'll have more arguments about the domain and range for the tangent and cotangent values eventually, but at least you have an idea of why we could see the whole range of values thinking through what we were just talking about. Okay. Then we talk about what's called the period for a function. So a function is said to be periodic if there's a number that we can add to the input to not change the function value. So if it basically repeats its function values on a certain interval. The trig functions are periodic, and whatever the smallest interval for the repetition is, that's called the period of the function. So if we think about the unit circle, the same point will correspond to several different angles. So if we're at a certain angle theta, we're going to land the same place whether the angle is theta or theta plus 2 pi or theta minus 8 pi. They're all going to land at the same point. right? So we can tell that cosine and sine have the same value if we add 2 pi or 8 pi or 20 pi, any multiple of 2 pi to the input. So we've got sine of theta plus 2 pi equals sine of theta. And there's not a shorter interval over which those values are going to repeat. So the period for the sine function is 2 pi. The sine values are going to be positive, then negative, then positive, but then restart. Sorry, positive, and then negative, and then restart. Same thing for cosine. But for tangent, we know the tangent values in quadrant 1 are positive, quadrant 2 they're negative, quadrant 3 they're positive again, and quadrant 4 they're negative. So the tangent values actually repeat faster. They repeat on a length of pi. Same for the cotangent values. So here we say the period for this function is 2 pi. Here the period is also 2 pi. Here the period is pi because they start to recycle faster. And then the secant and cosecant are reciprocals of the cosine and sine. So if one function has period 2 pi, its reciprocal would also have the same period. So cosecant of pi, theta plus 2 pi would be the same as cosecant of theta, and secant of theta plus 2 pi is the secant of theta. So those also have period 2 pi. So most of these functions have period 2 pi. Tangent and cotangent happen to have a shorter period because they start to repeat on an interval of pi instead of an interval of length 2 pi. So the conclusions that we got are right here. So if I want to find the exact value of sine of 21 pi over 6, I know my reference angle. Oops. Is going to be, well, let's see, we could actually reduce that, couldn't we? 21 pi over 6 is, we reduce it the same as, we can in fact take a factor of 3 out of both of those, 7 pi over 2. So my reference angle is pi over 2. Right. So I know I'm thinking about this point and then getting the right quadrant. Like, so which multiple of pi over 2 are we looking at? 7 pi over 2 is, let's see, 2 pi would be 4 pi over 2. So 7 pi over 2 would be almost 8 pi over 2, right? 8 pi over 2 minus pi over 2. So this would be 4 pi minus pi over 2. So 4 pi would be 2 revolutions, or pi over 2 short of 2 revolutions. So once around, twice around, pi over 2 short of that. So we're actually going to land down there at 0, -1. The sine value is the y-coordinate. So we'd say sine of 21 pi over 6 is the same as sine of 7 pi over 2, which is -1. I want tangent of 5 pi over 4, we know that the period of tangent is pi, so we could say that's the same thing as tangent of pi plus pi over 4, and that's the same thing as tangent of pi over 4. Because the period for tangent is pi. Tangent of pi over 4, we want to think about this point, square root of 2 over 2, square root of 2 over 2. We want the y to the x, the ratio of y to x, so we would just get 1. Or we can think about, if we're not using the period, we could use just this point over here in quadrant 3 that has those coordinates both negative, and that ratio is also going to be 1. So either you can use the period and split pi off, or you can say, oh, 5 pi over 4, that's going to land me over here in quadrant 3 and figure it out that way. There are different ways to deal with this. So we've already kind of talked about this in the last lecture, but let's think about the signs of the trig functions in each quadrant. Here in quadrant 1, x and y are both positive. In quadrant 2, x is negative, but y is positive. In quadrant 3, both are negative. And in quadrant 4, x is positive again, and y is negative. So, in quadrant 1, sine of theta is positive, cosine of theta is positive. Everything's positive because x and y are both positive, right? So let's just say that all are positive. In quadrant 2, anything that involves x is going to be negative, right? So cosine involves x, and tangent involves x, and secant involves x, and cotangent involves x. But sine and cosecant only involve y. So sine would be positive and cosecant positive. But the key is to remember what the sign is on x and y, and then how the trig functions are related to x and y, and then just go with that. In quadrant 3, x and y are both negative, so those ratios of x to y, like tangent and cotangent, would actually be positive, because the ratio of x to y will be positive, even though both are individually negative. X is less than 0, so cosine of x, or cosine of theta, is negative. Y is less than 0, so sine theta is negative. And the reciprocals would also be negative. And then finally, in quadrant 4, x is positive, so cosine of theta is positive, secant of theta is positive. Y is negative, which means that sine, which is the y-coordinate, would be negative, and its reciprocal would be negative. And the ratio of x and y, we'd have a positive to a negative, so both tangent and cotangent would be negative. So if we're given the signs for 2 of the functions, like we are here, we can figure out where the angle theta is located. So cosecant of theta, that's 1 over the y-coordinate, is positive. That means the y-coordinate is positive. Tangent is negative. That means that y to x is negative. But if y is positive, and y divided by x is negative, that information together tells us that x must be negative. So if y is positive and x is negative, that means we're going to be over here in quadrant 2. Right? So given two of those signs, we should be able to determine the location of the angle theta. So we've been using these identities all over the place, that cosecant is the reciprocal of sine because sine is the y-coordinate and cosecant is the reciprocal of the y-coordinate. And secant is the reciprocal of cosine because cosine is the x and secant is the reciprocal of the x. And the same thing, the relationship between cotangent and tangent. So those are called the reciprocal identities. And then we've also got what are called the quotient identities, that tangent of theta is the sine of theta divided by the cosine, because sine is y and cosine is x, and tangent is y divided by x. And cotangent is the cosine divided by the sine, because cosine is x and sine is y. So those aren't really anything super new. We've been using them throughout. We just haven't formally named them as the reciprocal identities and the quotient identities. This example 4, we could probably use a little more space. It's a little bit hidden here, but if we're given that sine theta is negative 2 times the square root of 2 over 3, and the cosine of theta is 1/3, we want to be able to figure out the value for the remaining trig functions of theta. And we can do this using those reciprocal identities and the quotient identities. First, think about which quadrant are we in. If sine is negative and cosine is positive, we must be over here in quadrant 4. Alright, so if we've got sine theta and cosine theta, then we can do the reciprocals of those. Cosecant is the reciprocal of sine theta. In this case, that's just going to look like negative 3 over 2 times the square root of 2. We'll rationalize it. So we'll have 3 times the square root of 2 over 4. Oops. Negative 3 times the square root of 2 over 4. And secant would be the reciprocal of sine, or cosine. So in this case, that's 3 over 1, or just 3. Let's see, the tangent and cotangent will get a little messier. Tangent of theta is the sine of theta divided by the cosine of theta. So we'd have negative 2 square root of 2 over 3 divided by 1/3. So negative 2 times the square root of 2 over 3 times 3 over 1. So the 3's would cancel. We'll have negative 2 times the square root of 2. And then finally, cotangent of theta. We want cosine divided by sine. So we'll have 1/3 divided by negative 2 square root of 2 over 3. So we'll multiply by the reciprocal of the denominator. The 3's will cancel and we'll have to rationalize that denominator. So we'll have negative 1 over 2 square root of 2 times square root of 2 over square root of 2. Negative 1 times the square root of 2 over 4, because we'd have 2 times 2. Alright. Then what we have are called the Pythagorean identities. These are, the first one is familiar, and the other two will be used throughout, especially in Calc 2. You'll use these a lot. We'll use them a lot in this course as well, obviously. But these just follow from the idea that if we're on a unit circle, x squared plus y squared has to be 1. So since x is the cosine of theta and y is the sine of theta, we know that cosine of theta squared plus sine of theta squared is 1. Right? So the proof of the first one is just using that unit circle relationship. And for the other two, if we start with cosine squared plus sine squared equals 1, and we divide it all by, let's say we divide it all by cosine squared, then we have the second identity, right? 1 plus tangent of theta squared is secant of theta squared. And if we divide, instead of dividing by cosine squared, if we divide by sine squared, we'll get the other one. So if we start with the first identity and divide everything by sine squared, that's going to lead us to cotangent of theta squared plus 1 equals cosecant of theta squared. Right. So I would recommend memorize the first one and then be able to use it to establish the other two. You don't need to memorize all three of them, just memorize the first one and then know how we got to the other two. Okay. Alright, so then here are just a few examples using those identities. You can see here the first one involves a secant squared and a tangent squared with the same input, right? So what we can do is notice that from above, if we rearrange, we could have secant squared theta minus tangent squared theta equals 1. So it doesn't matter what theta is. This is true for all inputs. So even if the input is 53 degrees, we don't care. But secant squared of anything minus tangent squared of that same thing is 1. So this is 1. The next one is a little trickier because the inputs aren't the same exactly. But we can say at least that this would be 1 over cosine of pi over 13. And then we've got cosine of 25 pi over 13. (25 pi over 13), let's think about this. So 2 pi would be 26 pi over 13. Okay. So this would be pi over 13 short of 2 pi. But if that's our angle, 26 pi over 13, notice that if we take pi over 13, those are going to have the same cosine values. Because the x-coordinate would be the same no matter which of these two angles we have, whether we're looking at pi over 13 or whether we're looking at 25 pi over 13. Right? The y's would be different, the sine values would be different, but the cosine values would be the same. So here we can replace cosine of 25 pi over 13 with cosine of pi over 13 using the symmetry that we can see from that picture, and we'll just get 1 from that. Alright, then cosine of 70 degrees divided by sine of negative 430 degrees. Negative 430 degrees we want to think about. That would be negative 360 plus negative 70. right? So we could replace sine of negative 430 with sine of negative 70, because we've got a rotation of 360 and then 70 more past that. So we could have sine of negative 70. And then we've got cotangent of negative 70. So we've got, it looks like things that are looking close to the same as each other right now, right? We've got cosine of 70 divided by sine of negative 70. We've got cotangent of negative 70. Cotangent of negative 70 would be cosine of negative 70 divided by sine of negative 70. So we could rewrite that. And then we want to think about 70 degrees versus negative 70 degrees. We rotate 70 degrees or negative 70 degrees, the cosine values are going to be the same, right? Because it's the x-coordinate of that point. So really what we could do is say whether we have a 70 or a negative 70, the cosine is the same, so that we can get these to match up. And then we've got two of the same thing. So we could at least say 2 times the cotangent of negative 70 degrees. It's not a very satisfying answer, but at least it's simpler than what we had at the start. Let's look at example 6. So if sine theta is negative 5/13 and we know theta is in quadrant 3, that should be enough information with all of our identities and relationships to figure out the values for the rest of the trig functions of theta. So we've got some point over here in quadrant 3. In quadrant 3 we know x is less than 0 and y is less than 0. Right? We usually want to use one of the Pythagorean identities to get started if we only have one trig function. So here we'll use the one that involves sine theta. So we'll have negative 5/13 squared plus cosine of theta squared is 1. This would be 25 over 169. And we want to subtract that from both sides. So I'll rewrite my 1 as 169 over 169. It's going to leave me with 144 over 169. So we've got cosine of theta is either positive or negative square root of that, which would be 12/13. Because we're in quadrant 3, we know we want negative. Right. So now we know sine theta and cosine theta. That should be enough to get us all of the others, right? So sine theta given was negative 5/13. Cosine theta that we figured out using a Pythagorean identity is negative 12/13. And cosecant is the reciprocal of sine, so negative 13 over 5. Secant is the reciprocal of cosine, negative 13 over 12. Tangent is the ratio of sine to cosine. Which is going to be positive 5 over 12. And cotangent is the ratio of cosine to sine, or the reciprocal of tangent. Either way, we should get 12 over 5. So starting with the Pythagorean identity to get one more trig function value, and then using the reciprocal identities and the quotient identities to get the rest. Example 7 here is another one where we could probably use a little more space, but it's similar to example 6. It's just a little trickier because instead of being told the exact quadrant, we're given a value for cotangent, and then we're told the sign, S-I-G-N, of the sine function. So again, if we've got the cotangent value, what we want to do is use a Pythagorean identity to get started. And the one involving cotangent, we could go and look it up, or we could start with the one we know. This is what I would do. If I want to get to cotangent, I want to have a cosine divided by a sine. So I'd divide this all by sine squared. And that's going to tell me cotangent squared plus 1 is the square of cosecant. So cosecant of theta squared is 1 plus cotangent of theta. We'll use that to get started. So in this case, cosecant is 1 plus, so cosecant squared is 1 plus 16/9. So 9/9 plus 16/9 comes out to 25/9. So we've got cosecant is positive or negative square root of 5/3, or sorry, square root of 25 over 9, which would be 5/3. And since sine is negative, we know the y coordinate is negative, and this is the reciprocal of y, so that's also negative. So we know we want negative 5/3. So now we've got cotangent is 4/3. Cosecant is negative 5/3. If we've got cosecant, we could get sine. That would be the reciprocal of this, so negative 3/5. Okay. And let's see, the others are going to be a little trickier to get than they were in the last example. Cotangent is cosine divided by sine. Right? So if I want to know cosine, I could do sine times cotangent. Right? So if I do cosine is sine times cotangent, I have those values. I'd have negative 3/5 times 4/3. Looks like negative 4/5. So cosine theta is negative 4/5. Now that I have those two, it's easy to get the rest. We just need secant, that's the reciprocal of cosine, and tangent is the ratio of sine to cosine, which looks like it's going to be positive 3/4, which we also knew by looking at the reciprocal of cotangent, so that fits the way we wanted to. So there are other ways to get through that, but that's at least one example of how we can work with the information that was given to get all the trig function values. All right, So the next example is a little bit strange, but it's just using the idea that the cosecant has period 2 pi. And using some symmetry. So if the function we're looking at is cosine of theta, or cosecant of theta, and we know whatever the angle is that we're looking at, the cosecant value is 2. If we rotate the opposite way, if this point up here was, we don't know the x, but the y is 1/2, because the cosecant is 2. That's the reciprocal of y, so then y would be 1/2. Then down here we'd have the same x, but the opposite y value, right? So the cosecant for the opposite rotation would be -2 instead of +2. Right? But if we add 2 pi and then add 4 pi, nothing's going to change to the function values. So we could say these are going to be the same as just f of a and f of a again. So we'll have 3 of that same thing, so we'd have 6. We've been looking at this symmetry and trying to figure out what will change if we change the direction of our rotation. That idea is tied to whether a function is even or odd. So what we should start with is some reminders. Just a definition. If f of the opposite input gives you the same thing as just f of theta, that's what's called an even function. But if you change the sign on your input and the output also changes, that's what's called an odd function. So those are the definitions of even and odd that you should have from College Algebra 1. So we want to know for each of these functions, of the trig functions, what's going on if we rotate the opposite way. So if I have theta this way, but negative theta that way, what will change for the function values? Well, if we think about it, we've got that point x, y, but if we rotate the other way, the x won't change, but the y will. That means if we rotate the opposite direction, which means make the input opposite, the signs that will change are on the things that involve the y-coordinate, right? So the sine function, the cosecant, the tangent, and the cotangent will all have opposite values. But the cosine and the secant won't change. Because those just involve the x-coordinate. So if we make the opposite rotation, the sine function actually will take on the opposite value. The cosecant will take on the opposite value. Cosine doesn't change, so we could leave this at cosine of theta. Secant doesn't change, so we could replace this with just secant of theta. Tangent, we get the opposite value. And cotangent, we get the opposite value. Okay. So that means this function is odd, and the only two that are even are cosine and secant. Okay, and then the last example here, example 9, we have just a combination of those functions and we have to determine whether it's even, odd, or neither. Notice one thing here, that the input changed. Instead of having a theta, it's an x, but that doesn't matter. We can name the input anything we want. So here we're just saying the input is x rather than theta, but it's not necessarily the x coordinate on the unit circle. Here we would think of x as representing the angle of rotation. So it's still just our input is like, think of it as like an angle or a distance we travel around the unit circle. If we want to know whether the function is even, we want to know, does f of negative of the input equal the same as if we just had the input x? Odd would be if we make the input opposite, then the function is opposite, and neither would be neither of those. Right? So our test is make the input opposite and see what happens. So we would make the input for sine opposite, the input for tangent opposite, and the input for cosecant opposite. And as we saw above, each of those is made opposite when we make the input opposite. So we would end up with the opposite of sine x plus tangent of x, and then the opposite of cosecant of x in the denominator. So we want to compare that with what we started with. We have the opposite numerator, and we have the opposite denominator, which means that we have actually the same thing as what we started with, since both the numerator and the denominator are opposite. So that's the same as our original function, which means the function is even. And the reason is, since when we made the input opposite, we got the same function back. All right, and that should be it for that section.